All right, welcome everyone to this week's Mechanical Engineering Research Seminar. Your speaker today is me, Micah Lande. I'll be talking about tinkering and learning and mechanical engineering. So bear with me, running tech and presenting. So we have some people online and I think everything's working. So I'll go ahead and get started. So I'm an assistant professor in the Department of Mechanical Engineering here at South Dakota Mines. I'm also the ER Census Chair for Engineering Education, and I appreciate that. I have a lab here that I call the Holistic Engineering Learning Lab and Observatory. Hello, how cute, right? And so my general guiding questions around research are twofold. What do designers do when doing design? And then how do designers learn when doing design? And so in mechanical engineering education, I see design as a number of different ways in which you could approach this. And this list is borrowed from Bill Moggridge, who was one of the co-founders of IDEO and then was director of the Cooper Hewitt Museum as part of the Smithsonian. And he was incisive in describing design is multi-layered, right? So the first might be that a recognition that stuff is designed, right? I go out and buy a car, someone decided that this yellow color or this red color was good for that. And then there's another layer on top of that that is the design process. And one could be mindful of how you step through a method to go about design activity. And then that third level being design practice. So how can one apply that design process in a better way, efficient way? And for me, what I'm looking at is more of a meta level of what do designers do when they do all of those things, when they're in practice, when they're applying their design process to stuff that is designed. And so my research comes from a qualitative research methods perspective, trying to understand and describe patterns of things, looking at a complex system that just so happens to have a person or a team of people doing design work in it. And so I borrow stuff from learning sciences and education, design research, and engineering education research. So I'll try to, one of my areas is looking at design thinking. So how might we understand what happens when people do design, and can we approach mechanical engineering design process by to broaden participation and look more broadly at empathy as part of what mechanical engineers do. Area 2 is around design education. So again, how might people learn design and prototyping and how we might help that along. And then 3, at a larger scale, what are larger educational systems and implications of curriculum and the like. And so I'll try to touch on each of these areas as I talk about my topic today. So here's my son, Bobby. He's almost 8, so he's in 2nd grade. And this is a picture from a couple years ago. He saw my wife and I installing curtains, and he was interested in using the cordless drill, right? And so it was an interesting thing of, you know, maybe he'll hurt himself, but really he just wants to drill holes in wood, right? He sees something he wants to try and do it. Here we told him that he couldn't drill the wood inside of the house. So he put the wood outside the house and enjoyed the air conditioning from inside the house, right? So here's some curiosity, maybe some practical ingenuity, and you know, he had hands-on experience building and making things. And I start with that because he's in 2nd grade now. We have him in a Montessori school, and as I understand Montessori education, it reflected on what my experience was as a mechanical engineering student and how I teach now. And so Montessori having an idea of starting with concrete materials, right? It might be as simple as having blocks that you put on top of each other. And then having abstract symbols. So my second grader is learning math, right? The numbers that are associated with that are abstract symbols. And then connecting that concrete and abstractness together. And so as I think about how this applies to mechanical engineering education, there certainly is a lot of abstract things that we introduce students to. So my freshman students have spent 3 weeks learning about statics and forces and moments and equilibrium. And those are abstract ideas, and trying to give them tangible, visceral experiences to play with materials, right? To tinker with materials. Prototyping is just playing with materials and brainstorming with materials beyond just ideas. And so this, as a perspective and balancing that concrete and abstract, is a starting point for me. And in this approach, there's a guy named Kolb who has described this as an experiential learning cycle. And so you could start anywhere in this learning cycle, start with the abstract, start with the concrete, but it's something that you go through, and in succession and iteration, you go from experimenting to observing, from the concrete to the abstract. And so to me, as a pseudo learning scientist, this is an interesting perspective, and maybe can use to dive into what tinkering might mean, but certainly prototyping and the oscillation between having an idea and imagining it and building and prototyping, creating, manufacturing it in a mechanical engineering context. So there's curiosity, right? And humor me as I start to go through and wax poetic about tinkering and some of these inputs, and then I'll dive into some specific studies that I've done that inform some of these perspectives. And this is still something, for me, forming of how tinkering might unify these different ideas, and hopefully today or a later point having some input and discussion from some of you all. Another starting point for me is in graduate school being involved in the academic pathway study that looked longitudinally and cross-sectionally at students at 4 different undergraduate institutions studying all sorts of fields of mechanical engineering. As part of this larger Center for the Advancement of Engineering Education. And one of the takeaways for me was some cross between intrinsic psychological motivation and professional confidence. So our students might be extrinsically motivated by getting an engineering job and a well-paying engineering job, but it's also, there's a group of people, and maybe a group of people we could bring into mechanical engineering who have some intrinsic psychological motivation. They want to make the world better. What better might mean, a different thing. But how can we have people who are inspired to have impact and make change with their mechanical engineering know-how? And to me, that underscores this curiosity thing. Another way in for me is prototyping. And so as my kid was excited to drill a hole in a block of wood and then wonder how long a hole from here to China would be, there's lots of maybe benchmarks for me and for you as well, right? So in thinking about tinkering, certainly MacGyver as a emblem of pop culture is something there, right? So a TV show, and I'll ignore the latest reboot, but basically you have Richard Dean Anderson, and there's a paperclip and some chewing gum, and he's able to get out of whatever situation there is very quickly. And some of that is a term of art that the National Academy of Engineering has introduced called practical ingenuity, right? And so when we come to problem solving within the mechanical engineering context, a lot of, I think, what we're getting at is practical ingenuity, particularly being able to manipulate materials and create things. So sometimes, you dive deeply into something and wonder where it will take you. For me, some of it is collecting examples of alpha prototypes or low fidelity prototypes that are historical case studies. So here on the left, you see part of an early transistor, right? So it's a low fidelity prototype. It maybe is functional. On the right there, you see a credit card. It's a piece of cardboard here with some magnetic tape from a audio cassette taped around the back of it. And to me, it's an interesting notion of practical ingenuity in prototyping. These are, at least for me in my background, a useful starting point to kludge something together or hack something together. So there's tinkering that's part of making and creating. In a wider engineering sense, an engineer plans and then enacts those plans. I think there's something that is interesting that is about the fungibility of what solutions you might imagine and what you might build as you play around with the materials and put together some ideas and make those things happen. So let me try to talk a little bit more about what I mean by tinkering, but mostly aspects of making and prototyping. So you're all, well, many of you probably have seen the Apollo 13 movie. I mean, it's based on a historical thing, right?
Situation brewing with the carbon dioxide.
We had a CO2 filter problem on the lunar module. 5 filters on the
problem,
which
right?
meant for
So
2 guys for a day and a half.
Filter,
So I told the doctor,
They're already up to 8 on the gauges. Anything over 15.
Putting around
Hair judgment, blackouts, the beginnings of brain asphyxia.
What about the scrubbers on the command module?
They take square cartridges.
And ones on the limb are round.
It's a hallmark, perhaps, particularly because it's captured so
Tell me
well.
this isn't a government
in
operation.
this movie.
It just isn't a contingency we've remotely looked at.
Those CO2 levels are going to be getting toxic.
Well, I suggest you gentlemen invent a way to put a square peg in a round hole.
Taking what you have, realizing that there's a constraint of materials,
listen up. People upstairs handed us this one, and we got to come through. We got to find a way to make this fit into the hole for this, using nothing but that.
Right. So there's some notion of creating something with a limited amount of materials. So here's a couple more examples. This is Eddie Van Halen's Frankenstrat, where he put together 2 different guitars to reach the sound that he wanted, right? Here on the right is another photo of that early transistor. On the left is an early prototype, alpha prototype of an Arduino microcontroller. On the right there, you have an early computer mouse. On the left, you have an early Palm Pilot, right? These are, in some cases, functional, but mostly exploring some subsystem of what it's like. Here's an early Super Soaker that was created and prototyped by an aerospace engineer, right? You see some of the, forgive me, crappiness of the prototype of found objects. Here are a couple more examples. On the right is an early prototype of the Rubik's Cube. On the left is the Nintendo Switch, which looks to be kludged together with some Wii remotes on the side of it. For me professionally, there was a version of this. This is a toy called the Agent Tracker that was developed as a toy under Wild Planet's Spy line. And the highlight for me professionally and personally was that it was featured on an episode of Scrubs.
What is that?
This here is an electronic hide-and-seek game. The other person wears a sensor, and the closer you get, the more it beeps.
Ah, funsies.
Yes.
And so here's an early kludged together prototype. I find it amusing just because in this photo I recognize other things. And so that handle is from a dog throwing toy. The white circular disc that those colored pieces of plastic are inlaid is the plastic base of a paper towel holder from IKEA. The receiver on the left is something else entirely. You know, here's another version of it, but we kludged together, hacked together things that worked as a way to prototype the idea and then sold it to, licensed it to Wild Planet, and then they redesigned it from the ground up to make more than one of them. So as I think about the word tinkering, it's a bit pejorative, perhaps. Here's an article from the New York Times talking about tinkering, but connecting it to making and maker spaces. And that's similar to how maybe I take a look at how to quickly prototype things to get an idea out, play with that idea through materials, and then think about how you might advance that solution. There's a term from an article in Design Studies from 1999 called bricolage, which I understand to be a French word, which is basically to take the items that are around you and put them together and make something new. And as a quick example of that, here's a project that I worked on previously. It was a personal heating and cooling device for the office, right? So there's a nice product photo on the right. At some point, we were playing around with how we might articulate an arm to dispense the warm air or cold air. And so we literally took a trash can that was next to us and turned it upside down and found other materials to put it together, right? So it wasn't very refined. We were exploring a very specific piece of what we were trying to do to understand what the experience would be like if you had air blowing on your face. But I like this as an example because we literally took a trash can and turned it upside down and then added some other things to it. And so I think that this is maybe a starting point for me, and then it's interesting to connect it to things that are emergent, like the maker movement or the maker community. And so some of my research in the past couple of years has been to try to explore the maker movement, maker community, and understand that and how that might overlap with mechanical engineering, engineering more broadly, and the educational enterprise of trying to teach engineering. So there's a notion of we're all makers. I've adapted that to we're all making engineers, so engineers who make and create things as a philosophical emphasis for me, but then also as educators reflecting on how is it that we're creating and building mechanical engineers themselves. So in my dissertation work, I was looking at what different mindsets of design and engineering, what mindsets of imagining the future, manufacturing there are, and how those relate to each other. One part of that was looking at prototyping pathways and how student design teams managed working through their projects from conception of an idea to making a proof of concept prototype, right? And so it was looking at examples of and archetypes of designerly ways of knowing and doing and thinking, and engineering ways of knowing, doing, and thinking. And so thinking about what the conceptual or experience would be as a designerly perspective, and then how to make functional a part or the whole system. And so more in depth about this, I could catch up with you outside of this talk, but it's, I think, illustrative to me of a starting point of trying to understand design teams, what activities they went through. These are all prototypes in some way or fashion, and how one can connect the activities that they're doing with their learning experience. And so my dissertation was focused on what their prototyping pathways were, but for me, a lot of the interest too was an extension of that, of different types of projects, whether it be ambiguous future-oriented projects or very optimizing technology types of projects. The pathway of the prototypes and the sorts of prototypes and the ordering of that was different. And so I looked at 9 different projects and tried to map over the year that students worked on these projecting teams, how those varied across the different types of projects. And really, there's a lot of jumbled design steps, right? So the design process as a linear thing is a teaching tool, right? As applied in practice, it's professional judgment that you internalize. And then the design process are steps, a bunch of tools that are in a toolbox that you jump around with. And so while I was doing this, a question of what is the engineer of the future, right? And how do we prepare our students to be prepared going out in the future? And so the National Academy of Engineering 2004 put together a report, some obvious things, right? Like analytical skills, flexibility, business, communications, let's see, what else is here? Ethics, leadership, professionalism, lifelong learning. And then there were a couple like creativity, practical ingenuity, and this is where I borrow the term from, come from. And so in trying to understand that, I was involved in the Bay Area with some do-it-yourself groups, and there are folks who call themselves makers. Back then, it wasn't as popular a term. It's been popularized by Make Magazine and Maker Faire. But looking at these do-it-yourselfers, these people who might not call themselves engineers who are building things, they are tinkering with technology, right? Playing with technology, curiosity, practical ingenuity, building prototypes that help explore or learn or solve problems that one cares about, right? So there's the curiosity inherent in that, the playing with the tinkering and playing with technology, practical engineering, building prototypes. It's about creating things and having maybe an end goal of building some sort of system that does solve some problem that you're interested in. So maker fairs have waned, but they are things that were quite popular for a while. I think this weekend there's a mini maker fair in upstate New York that brings together a bunch of who aren't necessarily engineers, who don't identify themselves as engineers. And there's, these are things that they might create in their garage, right? Here are some human-powered cupcakes. Here's another example, a hobbyist, right? Made a model of Yankee Stadium with toothpicks, right? Just think of how long that might take. It's an effort to create something and express a part of one's own personality, own soul, and connect. So, addressing problems that one cares about, it could be impractical, or it could be practical ingenuity that we're seeing here, right? So tinkering as a role of understanding how one might identify, imagine, and then build those solutions. So as part of some research that was funded by the National Science Foundation, a couple years ago, we started to look at the educational pathways of makers with this idea of understanding how engineering and making might overlap, with the idea maybe this is an ad hoc approach to project-based learning out in the wild, and it might be something that we could understand what we do in the classroom better, or to understand what we can do, what is exciting to people who are makers, and bring that back into the classroom. So a number of undergraduate and graduate students, this work engaged. We went to maker fairs. Here's one in the Bay Area. There's been another large one in the World Maker Faire in New York City. Of late, these have been more virtual. There was a virtual maker fair around the world in May that I participated in and talked about some of this research more in depth. But you could find all sorts of interesting widgets and stories behind those people. Here's a speaker made out of a mason jar, developed by someone who dove into understanding manufacturing and how to reuse everyday objects with adding some simple electronics. Here's a sculpture that has a number of motors here that move pieces on it. So a kinetic sculpture developed by someone who is very much of a mechanical engineer as a way to explore art. Here's all right. So as I was saying, all right, great. Technical difficulties. There's some examples of projects that we would see at Maker Faire, and I just share those to add some color. Here's a high five machine that is something that was at Maker Faire, but also something at Burning Man, right? And so some of these are things that overlap between art projects and engineering projects. But here are makers, and they're amateurs in maybe the best sense of the word. There was a writer, Barry Katz, who had a footnote in one of his books that talked about amateurs as being exceptional because they do it out of the love or passion of it, right? Not for any like specific monetary motivation, right? So the intrinsic psychological motivation. And the idea that it's a group of people who are doing it together, right? So again, with this idea of practical ingenuity, creativity, and being self-directed, right? These are all qualities that we would want our undergraduate students to have, and these are expectations that we might have for our graduate students, right? So there's a lot of design activity, engineering activity, imagining and making, right? So there's a number of examples of young precocious children when we're talking about engineers of the future. Kane, a couple of years ago, built an arcade out of cardboard and paper in his father's auto parts store. Zephyr is somebody who worked with evil scientist labs to make a watercolor painting robot, right? So here's and presented it at the White House Maker Faire. Joey Huddy is a young maker who also was at the White House Maker Faire a couple years ago, making a gun out of for marshmallows, right? So there's some amusement as he launches his marshmallow launcher in the White House, right? And so the interesting intellectual question to me is the pathways of these people. So we went and interviewed young makers and adult makers, and then also the parents of adult makers, to try to understand what knowledge, skills, and attitudes they possess that are related to engineering, and then how do the pathways of makers intersect with engineering, right? So we researched design, and I'll skip over that. But we went over to these two large maker fairs in the Bay Area and in New York City, talked to a couple dozen young makers and adult makers alike, tried to oversample for underrepresented groups. And so we went about asking questions, and we had interviews asking them about their artifacts, what the prototypes, what they made, and critical incidents, asking questions of how they got to where they're going and where they're going next, right? So artifact elicitation, tell me about what you brought, what did you need to learn to make these, how did you come up with this idea? Critical incident, right? Tell me the story of how you became a maker. Where do you see yourself in 5 to 10 years, right? What are you going to major in college? So we went through a methodology where we did parallel inductive and deductive coding of these interview transcripts to try to generate theory. And so we identified some of these attributes of making, of sharing. It's an open collaborative environment. Practical ingenuity, right? There's value in being ingenious and creating things that don't yet exist or doing them in novel ways. There is some personal involvement. Here's Mario, who made a 3D printing pancake machine, right, on the behest and curiosity of his small children. There's playful invention, right? So practical ingenuity, but then also impractical ingenuity, right? Here's a fire-breathing octopus, of course, right? And that it's a community of people, and there's some curiosity in what you do so that you can share that so that other people might create it. And there's also an element to facing failure, right? So some of it is more process oriented about what did I learn as I was trying to make this thing work, and it never worked. But there is some advantage to learning from failure. And a lot of it is self-directed in nature, right? So my favorite example of that is a mother and son wanting to make a fire-breathing dragon. And so they built it out of their garage, learning what they needed to in a just-in-time fashion, right? So it's not like they had a thermodynamics book per se, right? But it was what did they need to know in order to make the thing that they imagined, a mission-based approach to what they were creating. And so one way in which we consolidated this was this idea of having a culture of additive innovation. And so the notion that you're inspired by the community, you build and share and learn recipes and iterate on those designs and share those back to the community. And so, in some ways, it's a Creative Commons open source kind of approach, but it's a startling difference between how open and collaborative people are here versus what you might see in a mechanical engineering classroom or any engineering classroom where there isn't as much collaboration, right? It might not even be additive. It might be more subtractive in nature. And so understanding making and engineering, certainly workforce development, broadening engineering pathways, informing our educational efforts, right? There are makers that are out there that maybe should be engineering students. There are engineering students who could benefit by learning through a making lens. And there's some bit of this that can be reflected through ABET or this vision of the engineer of 2020 of bringing some of these aspects of making into an engineering curriculum. And again, in thinking about tinkering, that idea of practical ingenuity and creativity and lifelong learning to me really resonate. So if you look at the maker community, there are a couple of things there. The engineer of 2020, those things are aligned. If you look at K-12 and 21st century skills, those things are aligned. And you look at ABET, and there's something missing there in that idea of creative confidence or creativity and innovation, right? And it's maybe a mission then of how to foster a culture of additive innovation, right? This kind of open sharing ethos. And I think that to me, there's a lot of interfaces between these different aspects of how one might think of creating and solving problems in the world, right? And so maybe there's something between how to make one of something and how to make many of them. So makers do engineering, and then it's an interesting context to take things away. Let me try to quickly cover a couple other related studies around tinkering and making and building. One is looking at prototyping and what are the conceptions of students and faculty around prototyping. And so, a big takeaway for me is trying to understand what sophomore engineering students and their instructors think about prototyping. And I summarize it here as a quote from a student, really making me think of, do students think about prototyping as part of the process, right? It's a step in the process, but the prototype is something that is not functional. So it's a fallback, right? So the way it turned out, the student says, it didn't turn out exactly how I wanted. So I definitely consider it more of a prototype now. So in trying to understand conceptions of prototypes, this is a work done with a student, Hadi Ali, looking at how students describe prototyping conceptions in engineering design, right? So we did the same kind of thing, artifact elicitation and photo elicitation. And some of I'll share with you are some of the themes that came out of those conversations, right? So here's a quote from a pseudonym, Charlie. A while back, I had 3D printed sort of a keychain. It was based on an artifact from a game I like, so I wanted to make a keychain version of it, right? So prototyping as a way to be inspired, navigate ambiguity, gain insight. We went and approached this. What have people said about prototyping in the design process? right? Early or throughout the process, experts versus novices, some other things, communication, feedback for designers. And so we saw a gap in literature and an opportunity as it relates to student learning. And so artifact elicitation, some semi-structured interviews. Here are some of those types of questions. And so the students identified things talking about the level of complexity, right? So as a prototype of really a simple mechanical system, design problems, right? As a prototype, looking at the shape and function, right? So we're looking at the design process or the level of complexity or the prototyping process, and then some other things, constraints and the like. And I'll skip over some things. But it's interesting what counts as a prototype, what is valued as a prototype, the benefits and challenges of prototyping and in-class and out-of-class prototyping. So here's Charlie again. Originally, it would have been considered a final product, but with the way it turned out, it didn't turn out exactly how I wanted. So I definitely consider it more of a prototype now, right? And so as I think about values associated with design work, certainly iteration and different scaffolded prototypes along the way, because what one imagined, it didn't come out to fruition, it wasn't successful, then it's something lesser than a prototype. And to me, it's an interesting thing of, well, what if there's ingrained a value of making multiple prototypes and along the way? Here's another student, Andrew, a simple, less complex prototype, right? Here's a student talking about their learning and putting their hands on things to observe what happens. To me, this is more of an approach to tinkering or a making mindset. Didn't have time to implement it, right? So it's done here in school, but it's done in the classroom, not outside of that. So their students report that their actual design processes are different from a formal design process, right? So it being messy, right? There's ways in which we instruct students to go about doing design work, and then because it's a little bit less or it's become messier, right? The students rectify that to tell their story instead of embracing kind of the uncertainty and ambiguity therein. So time is also a constraint of the prototyping process. We also asked faculty about their conceptions of prototyping, right? And so the design process as something they're supposed to learn in class. For me, the biggest challenge, we have that end goal, but for many teams, it's putting it in the report. A lot of times that process is not written down, right? So they may be tinkering, but they rectify what that process is along the way. Another faculty's comment, we provide very little guidance. We provide no guidance in terms of materials or fidelity. And so to me, there's something here in tinkering in the design process that has some value. So students underutilize prototyping and don't consider it as part of the design process. And so trying to think about how we might, as educators, scaffold design activities and help them along the way. So the other interesting thing to me is this idea of learning trajectories. And so how we might capture the mental models of students in their design process to reflect some of these things, but also recognize that there is a path from novice to maybe adaptive expert about the design process. And so, all right, so all right. So I have some voiceover here. Let me skip over that for the purposes of time to get to something more specific. All right, and so here are some examples of student design process drawings before and after. In this case, it's a master level mechanical engineering design course. And in some ways, not much, in some examples, there's a dramatic shift of learning. Here's a student who has, on the left, you see before, and on the right, you see after. And so there's a linear process, and then there's a loop back that says iterate. Or here's another student and how they add some recursion within the design process. Here's somebody who had a more colorful starting point on the left, and then those arrows go both ways on the right. Here's another example of a more circular design process, and then what gets presented at the end is something that is a little bit more experiential. And so to me, it's an interesting thing of the design process and what students learn and might present back of what the procedure is versus how they might apply it in strategic knowledge. And so here is another one that maybe goes from, here's an iterative circular design process concept map to something that is more reflecting the experience and strategic knowledge. So here's another one. Certainly there's a lot of iteration represented on the left. On the right, there's A and B, and then A prime and B prime, so that it reflects some of that experience as well. And here's another one that goes from mostly a linear process to one that's more experiential. And so to me, it's an interesting thing of how might we conceive of and represent a design learning trajectory of applying a design process as routine, and then something that is adaptive. And so I'll finish here, but the idea that tinkering is a viable approach to problem solving, right? It's grounded in maybe some historical examples. It's grounded in what people actually do when they go through the design process. But students, as learners, they are introduced to the design process and prototyping and other things that might be associated with it in a much more straightforward way. And so the ambiguity that actual design activity and prototyping actually takes, to me, is an interesting thing that might reflect tinkering as an exploration and the messiness of a design process there as a viable way to learn mechanical engineering. So I'll stop there. We're about out of time. I think there's some time for questions. If anybody out there right now wants to unmute themselves and ask questions, or if there are questions in the room, we probably have about 5 minutes. Thank you.
Very much. I do have a question, please, Chairman.
Yeah, go ahead.
Okay, so I'm going to forget the terminology used, but design learning.
A design learning trajectory. Sure.
Okay. So I understand and appreciate the desire and the value in studying design learning trajectory in undergraduate education. One of the challenges, I think, is inherent in engineering education. We're trying to get them ready and get them prepared to be productive, successful engineers. Are you or other folks doing any studies about what happens to that design learning trajectory after school?
Right.
Are there focus groups and studies looking at the successful design engineer with 20 years experience?
Right. So there's work aligned to what I'm doing that has looked at practicing engineers. And that is where most of this interest has started from, right? You could go into a company and embed yourself in a design team and follow them maybe more easily than you can with a student who's in multiple classes in college. And so the idea of this trajectory being, here's a freshman, right? And then how do you develop that fluidity or literacy with a design process, and then beyond school? Like there's a trajectory that I think on the other side is someone who's an adaptive expert, right? And so, oh, I'm a practicing engineer. I've seen a case like this design problem before. We don't need to go and do all of this research or all this work. We could just leverage what we've already learned, right? And so there's the idea of having developed expertise when it comes to like a technical body of knowledge, but also being able to recognize, and maybe it's another question of synthesis of how things might relate. So there's some interesting work in looking at practicing engineers and the idea of knowledge brokering, in that you take what you've learned in one project and are able to recognize it and apply it in another, right? And so in some ways, the benefit of being a practicing engineer is that you have a lot of experience and a lot of a library of experiences that you could pull on. In trying to think about what that might look like in an educational setting, people have generated this as a question of future work, right? So this is how practicing engineers work, or this is how novices work, but not so much how does one transition from being a novice to being an adaptive expert. And it's a curious thing of students when they graduate as undergrads, they're by no means adaptive experts, right? But they're much more knowledgeable about these types of things in work practice than when they're first year students, right? And so it's interesting to see teaching design and seeing what students do in like our ME 110 class versus mentoring a capstone team, right? And some of it is, I think, coming back to an idea of creativity and being self-directed, right? There's practical ingenuity in there as well, perhaps. But my graduate work was at the Center of Design Research at Stanford, and so some of that was looking at these graduate students as a proxy for practicing engineers. Some people looked at designers in all sorts of different ways and practicing engineers. To me, it's an interesting thing of taking the work practice and understanding what maybe learning happens across the undergraduate education around design. Cool. Thanks for the question.
Thank you.
All right. Anyone out there also have questions? We have maybe another minute or two, or I'm happy to talk about this type of stuff offline. Of course, I tried to squeeze in too much stuff, and there's stuff that I didn't tap on. The idea of tinkering and how that might fit into maybe a more rigorous context of mechanical engineering education, to me, is an interesting tension. There's maybe more flexibility in looking at design with practitioners out in the workforce, or looking at K-12, right, as art and craft and the like. All right, so I'm out of time, but if there's a question or two, since I'm facilitating, it doesn't seem like there is, though. All right, this might be a good place to end. Thank you for your time and attention.
Thank you. Good job.
All right. All right, thank you for attending.
We'll see some of you next week.